Today we're going to talk about normal operators. First, let's review some concepts from previous lessons. We'll start with the complex numbers. Let's denote I as the square root of minus 1 as a root of the polynomial f of t equals t squared plus 1. Recall that we'll denote bold letter C as the collection of complex numbers, which are numbers of the form a plus bi, where a and b are real numbers. We found before that the set of complex numbers under addition and multiplication forms the field. We also found the fundamental theorem of algebra, which states that every polynomial f of t with coefficients that are complex numbers has a root in the complex numbers. In particular, if A is an n by n matrix with coefficients in the complex numbers, then its characteristic polynomial also has roots in the complex numbers. We found the following result, which explains how to compute the eigenvalues of a linear transformation T. Say that V is a finite dimensional vector space over field F and that we have a basis beta. If we let T be a linear transformation, we'll denote A as the matrix representation of T with respect to this basis beta. We found that T is diagonalizable if and only if there exists an ordered basis beta consisting of eigenvectors of T. Furthermore, if T is indeed diagonalizable, then the matrix representation A with respect to this ordered basis of eigenvectors is a diagonal matrix, and the diagonal entries are the eigenvalues associated to these eigenvectors. We also found that the following four statements are equivalent for any scalar lambda. First, lambda is an eigenvalue for our linear transformation T. Second, lambda is an eigenvalue for our matrix representation A. Third, the determinant of A minus lambda in equals 0. And fourth, there exists a non-zero vector lowercase v that exists in the eigenspace for lambda. That is the null space of the linear transformation T minus lambda IV. With all of this, we then see that the n by n determinant of A minus T in is a polynomial of degree n which is independent of the choice of basis beta. In particular, any linear transformation T on a vector space V of dimension n has at most n distinct eigenvalues lambda. In the last lesson, we discussed how to possibly consider a line which gives a good approximation to a set of data. Indeed, say that we have a set of data which consists of points t1, y1, t2, y2, and so forth. Then the best linear fit, that is a line y of t equals ct plus d, has coefficients c and d as you see here on your screen. The normal equations are the equations that you see here. Here we multiply a 2 by 2 matrix that consists of the sum of the t sub i's times our two-dimensional vector cd will equal to another two-dimensional vector which consists of the sum of ti times yi. There's another way to view all of this. We have the following matrix products. Let's consider a matrix A, which consists of these various time steps. That is, it has two columns, which consist of the ti's and the number 1. Similarly, we can consider Y, which is a column vector, which just consists of the y sub I. Then if we consider the matrix product A star times A, we find the 2 by 2 matrix, as you see at the top of your screen. And similarly, if we consider A star times Y, we have a two-dimensional vector that you see at the upper right-hand part of your screen. So the idea is that we're trying to find an approximate solution to the equation ax equals y, but we can simply multiply on both sides by a star to find a slightly different equation. That is, the system of two equations and two unknowns is really equivalent here to a star a times x0 equals a star y. Let's state this in a slightly different way. When either f is the real numbers or the complex numbers, our finite dimensional vector space f to the n is an inner product space with respect to the standard inner product. Let's say that A is an m by n matrix and y is an m-dimensional vector. We cannot expect to find a vector x such that A times x equals y, but we can and do seek a vector x0 such that the norm of the vector ax0 minus y is as small as possible. Indeed, that vector is given by a star a inverse times a star y. We'll give a definition. Let's say that A is an m by n matrix. Then the expression a star a times the vector x0 is equal to the vector a star y will be called the normal equation. To explain the most general solution that we can have, let's consider a finite yet very large sampling of points m along a curve at various times. So at t1, we may have the point x of t1, y of t1. At time t2, we may have x of t2, y of t2, and so forth. So more generally, say that we have a curve gamma where we have this collection of points x of t and y of t. Say that we'd like to fit a polynomial of degree n minus 1 that goes through these m points. Since m is considered to be very large, we can really express everything in terms of integrals. So here, the coefficients c1, c2 through c sub n can be expressed as the inverse of an n by n matrix times an n-dimensional vector. Here, the entries are given by the integrals of a power of x of t times y of t, where we're approximating our sums over these m points with an integral. Before we really begin today, let's start with the motivating example. Let's say that C2 is the complex plane. Recall that this is a finite dimensional inner product space with respect to the standard inner product. Let's fix a real number theta. Recall that the following linear operator from V to V is a rotation counterclockwise about the origin via an angle theta. We'll recall also that beta, consisting of E1 and E2, is the standard basis for our vector space V. With respect to the standard basis, we see that we can write a matrix representation of our rotation as the 2 by 2 matrix cosine theta minus sine theta, and cosine theta. It's easy to see then that A times A star is equal to the identity matrix, which is also equal to A star times A. In all of this, even though we're working over the complex numbers, we actually see that our matrix A is a real matrix. This is one of the concepts we'll play off of today, whether or not we're dealing with the real numbers versus the complex numbers. To this end, let's actually focus a little bit more on the complex structure of this matrix. Instead of considering the standard basis as before, let's consider a slightly different basis in terms of these new vectors e1 prime and e2 prime. We see then that this new set of vectors forms a new basis for our vector space C2. In fact, if we start with an old vector x comma y, we can actually express this in terms of a new vector x prime, y prime, where x prime is x plus iy, and y prime is x minus iy. Recall that then we can express now the change of coordinate matrix Q by simply placing in as the columns of Q our vectors e1 prime and e2 prime. This really means that we can express our vector x comma y as Q times the new vector x prime comma y prime. Putting all of this together, let's consider now the new matrix B, which is the matrix representation of T with respect to the new basis beta prime. We can express this as the product involving the change of coordinate matrix Q. That is, B equals Q inverse AQ. And now we see that B is a matrix involving complex numbers. That is, we have cosine theta plus I sine theta, 0, 0, and cosine theta minus I sine theta. In a future course, you'll see that cosine theta plus I sine theta is equal to e to the I theta. This is what's known as Euler's identity, but we will not cover this in any detail here in this class. We do see, however, that this matrix B with complex entries is a diagonal matrix. In particular, our rotation by an angle theta is a diagonalizable operator. Let's consider this in more detail today by discussing a general concept known as normal operators. Say that V is a finite dimensional vector space over either the real numbers or the complex numbers, and let's fix an inner product on V. A linear operator T from V to itself is said to be normal if T composed with T adjoint is equal to T adjoint composed with T. We'll see later many examples of such an operator. But first, let's try to state a few properties. Say that T is indeed a normal operator on a finite dimensional vector space V. Then the norm of T of x is equal to the norm of the adjoint of T applied to x. In fact, this statement really motivates why we call this a normal vector. The idea is that the norm of T of x is the same as the norm of the adjoint of T on x. Next, if T is a normal operator and C is any scalar, then T minus C times the identity transformation is another normal operator. Next, say that x is a vector in our vector space V, which is an eigenvector of the linear operator T. And let's say that lambda is an eigenvalue corresponding to this eigenvector. That is, T of x equals lambda times x. Then x is also an eigenvector of the adjoint of T, but now the eigenvalue is the complex conjugate of lambda. That is, T star of x equals lambda conjugate times x. Finally, say that x1 and x2 are two eigenvectors of T corresponding to two distinct eigenvalues, lambda 1 and lambda 2. Then our vectors x1 and x2 are orthogonal to each other. Let's begin by showing the first statement. For any x in our vector space V, we'd like to consider the square of the norm of T of x. We know from the definition of the norm that this is equal to the inner product of T of x with itself. But now, by considering the property of the adjoints, we can slide T from the right over to the left, and we realize that T star T is equal to T T star because T is a normal operator. Now we can slide T to the right and replace that with T star, and we realize that by definition, this is the square of the norm of T star of x. Let's show the second statement. For any scalar C, let's denote the operator U as T minus C identity. Then we can consider U star in terms of C minus C IV and T star minus C conjugate IV. Upon expanding this out using the distributive property, we now see that we can swap T T star with T star T. And using this argument all over again, we can now factor to see that this is equal to U star U, showing that U is indeed a normal operator, assuming, of course, that T is a normal operator. Now let's show the third statement. Assuming that T of x equals lambda x, as before, let's let U be T minus lambda IV. Now we know that U of x equals the zero vector because we're assuming, of course, that x is an eigenvector of T. This means that the norm of T of x should be zero as a scalar. But we've just shown that the norm of T of x is equal to the norm of T star of x whenever T is normal. So in this case, the norm of U of x is equal to the norm of U star of x. But now we realize that U star of x, U star is T star minus lambda conjugate, so we have the norm of T star of x minus lambda conjugate times x. But of course, the norm is non-degenerate, so this does indeed show that T star of x equals lambda conjugate times x. We'll finish off the proof by showing the fourth statement. Say that x1 and x2 are eigenvectors of our transformation T corresponding to two distinct eigenvalues, lambda 1, lambda 2. Let's start with the expression lambda 1 times the inner product of x1 and x2. We can bring the scalar lambda 1 inside of the inner product because, of course, the inner product is linear. Now we use the fact lambda 1 times x1 is T of x1, and we can bring T to the right-hand side and make this T star by the definition of adjoint. We've already seen that t star of x2 should be lambda conjugate times x2 by the previous statement. And of course, now we know that we can swap lambda 2 outside of the inner product by essentially linearity and symmetry put together for the inner product. So upon subtracting the left-hand side from the bottom, we see that we have the scalar lambda 1 minus lambda 2 times the inner product of x1 and x2 must be 0 as a scalar. But lambda 1 is different from lambda 2, so we must have the inner product of x1 and x2 equals 0, showing that indeed x1 and x2 are orthogonal. Let's use all of this to write down a few more properties. Let's say that T is a linear operator on an n-dimensional space, and for the moment we are not assuming that T is a normal operator. We have the following classical result by a German mathematician, Isai Schur. Let's assume that the characteristic polynomial of T splits over F. That is, we can write the characteristic polynomial as a product T minus lambda 1 to some multiplicity m1 times T minus lambda 2 to some multiplicity m2, and so forth. That is, the characteristic polynomial factors as linear factors where we have eigenvalues in the field F. Then there exists an orthonormal basis beta for V such that the matrix representation of T with respect to beta is upper triangular. Here, please remember that we are not assuming F is the complex numbers. Indeed, the fundamental theorem of algebra states that if F is the complex numbers, then this statement is always true. That is, f of t always factors into linear factors. However, if f is the real numbers, then this statement here may not be true. It is not always true that the characteristic polynomial factors as linear factors. Indeed, let's consider the special case where f is the complex numbers so that we do know that we have a factorization in this form. Then T is a normal operator if and only if there exists an orthonormal basis beta for V consisting of eigenvectors of T. Let me remark how this is related to what we've shown in previous lessons. We've shown that T is diagonalizable if and only if there exists a basis consisting of eigenvectors of T. The difference between being diagonalizable versus being normal is that normal happens if and only if this collection of eigenvectors forms an orthonormal basis, not just a basis. We'll see more properties of this in the breakout sessions later today. Let's first prove the first statement by induction on n, the dimension of our vector space. Let's consider the following proposition, P of n. For any linear operator T on an n-dimensional vector space V such that its characteristic polynomial splits over F, there exists an orthonormal basis beta such that the matrix representation of T is upper triangular. Let's establish the base case when n is equal to 1. Well, if T is a linear operator on a one-dimensional vector space, then this means that T must be a scalar. That is, T of x is simply lambda times x. And by definition, the matrix representation is just that scalar, which is, by definition, upper triangular. Let's now assume the inductive hypothesis. That is, let's say that proposition P of n0 is true for some positive integer n0. We'll now perform the inductive step. So let's consider proposition P of n0 plus 1. To this end, let's let T be a linear transformation from V to V on a vector space of dimension n0 plus 1. Since the characteristic polynomial splits over f as assumed, there must be at least one eigenvalue lambda for our transformation T. So let's denote x0 as an eigenvector. We know that T star of x0 is lambda conjugate of x0, so we will denote V sub n0 plus 1 not just as the eigenvector here of T star, but as the normalized eigenvector. That is, we'll take the eigenvector x0 and divide by its norm so that the norm of V of n0 plus 1 will be equal to 1. Let's now consider the subspace W, which is the collection of vectors in V which are orthogonal to this normalized eigenvector V n0 plus 1. You can also think of this as the orthogonal complement to the span of V in 0 plus 1. Now, for any t of x in R space W, we're going for any x in R space W, we will show that t of x must also be in this subspace W. Indeed, fix an x in W. Recall that the inner product of x with V in 0 plus 1 must be 0. Let's now consider the inner product of t of x with V in 0 plus 1. Using the property of the adjoint, we can slide t to the right-hand side to see that this is the inner product of x with t star of V in 0 plus 1. But recall that we were assuming that V in 0 plus 1 is an eigenvector of t star. So this here is equal to lambda conjugate times V in 0 plus 1. And we can move the scalar lambda out front to see that this is equal to lambda times the inner product of x with V in 0 plus 1. But x is in W, so this inner product must be 0, thereby showing that t of x must be in our subspace W whenever x is in our subspace W. This means that if we restrict our linear transformation t to the subspace W, then we have a well-defined linear transformation from W to itself. Now let's consider W in a bit more detail. We see that W must be the orthogonal complement to the span of a vector. The span of our vector must be a one-dimensional space, and since we're assuming that V is an n0 plus one-dimensional space, we see that W must be an n0 dimensional space. Now we can use the inductive hypothesis. Since W is an n0 dimensional space, we can find an orthonormal basis, call it gamma, such that the transformation, the matrix representation of our restriction T sub W is an upper triangular matrix. Let's stare at what this means. To be an upper triangular matrix means that if we apply T to every vector in gamma, then we see that we must have a sum as you see here on your screen. T of V1 must be a scalar times V1. T of V2 must be a scalar times V1 plus a scalar times V2, and so forth through T of Vn0 must be a scalar times V1 plus a scalar times V2, all the way through a scalar times Vn0. Now let's consider the last vector, Vn0 plus 1. Well, we've just realized that by definition, T star of Vn0 plus 1 must be lambda conjugate times Vn0 plus 1. This means that T of Vn0 plus 1 must be lambda times Vn0 plus 1. Using this now, we can then see the way that our matrix representations must work. Indeed, if we consider the matrix representation of our restriction TW with respect to gamma, we see here our upper triangular matrix. This we know must exist by the inductive hypothesis. But now, in adding in just one more vector, v in 0 plus 1, we see now that the matrix representation of T with respect to our new basis, beta, found by adjoining one more vector to our orthonormal basis, gamma, must consist of this column, which is 0, 0, 0, all the way through the last one, which is lambda. This actually does show now, by induction, that our proposition P of n must be true. Let's consider now the second statement of the proposition. Since V is a vector space over the complex numbers, the fundamental theorem of algebra states that every polynomial must factor into a product of linear factors. Assume now that there exists an orthonormal basis consisting of eigenvectors. Then we know that the matrix representation, A, is a diagonal matrix whose diagonal entries are the eigenvalues, lambda sub k. So the adjoint, A star, must be a diagonal matrix whose diagonal entries are the complex conjugates, lambda k conjugate. Now let's consider A star, as well as A star A. We see that these must be equal because this is a diagonal matrix whose diagonal entries are the norms, lambda k squared. So that if we consider A star minus A star A, we see that not only is this the zero matrix, but this must also be the matrix representation of the operator T composed with T adjoint minus T adjoint composed with T. showing that T composed with T adjoint must be equal to T adjoint composed with T, showing, of course, that T is a normal operator. Conversely, let's assume that T is a normal operator. By the statements above, we can find an orthonormal basis of our vector space V such that the matrix representation of T is upper triangular. It suffices to show now that each eigenvector V sub k, each vector V sub k, must be an eigenvector for T. We'll do this by induction. We'll denote P of M as the following statement. For each integer k between 1 and m, our vector V sub k is an eigenvector of T with eigenvalue A sub k. Let's establish the base case. Proposition P of 1 is true because remember we have an upper triangular matrix, so T of V1 must be A11 times V. This is by our choice. Let's assume now the inductive hypothesis. Let's say that P of M0 is true for some positive integer M0. We'll now perform the inductive step by considering proposition P of M0 plus 1. Let's now consider integers I and j less than m0 plus 1, where I will be less than j. First, let's consider the inner product of T of V sub j with V sub I. Recall how we've chosen our upper triangular matrix. The T of V sub j we can write as a sum, k goes from 1 to n, of A sub kj times V sub k. But now the inner product of V sub k and V sub I is pretty much 0 unless k equals to I because we have an orthonormal basis. So we see that the inner product of T of Vj with Vi is just the matrix entry Aij. Now let's consider Aij in a slightly different way. Since we know that this is indeed equal to the inner product of T of Vj and Vi, let's slide T over to the right and realize that we now have the complex conjugate Aii conjugate times V sub I. But we can pull out Aii as a scalar to see that this is Aii times the inner product of Vi with Vj. But remember again that we have an orthonormal basis, so this must be 0. But now putting this together, we see that if we take T of Vj, again, this must be the sum k goes from 1 to j of Akj times V sub j, but all of the Aij's are 0 unless k equals j. So T of Vj must be Ajj times Vj. But now this shows that T of V sub k must be Akk times V sub k, whenever k is between 1 and m0 plus 1, showing that proposition P of m0 plus 1 must also be true. But this now proves the proposition. Thanks very much for watching.